So I'm Breanne Christie. The research I'm going to be talking about today, I conducted at Case Western Reserve University, but I'm actually now at the Johns Hopkins Applied Physics Lab doing a postdoc. So today I'll be discussing an ambulatory searching task that we developed that reveals the importance of plantar sensation for lower limb amputees. So to start, what are some of the locomotor challenges that lower limb amputees face? Well, for starters, they often have difficulty negotiating over uneven terrain, stairs, and ramps. They have an increased fall risk compared to age-matched controls. And they often adopt an asymmetrical gait, meaning that they spend more time on their intact limb than on their prosthetic limb, which can over time lead to overuse injuries of that leg, and actually underuse injuries of the residual leg. So this sort of leads to the question, like all these locomotor challenges, what could be better? How can we make prostheses better in order to address these? Well, one thing that we know pretty certainly over decades of research is that locomotion is a sensory motor process. But really, a lot of the technical developments over the last several decades have focused very strongly on the motor component. So focusing on things like the design of the prostheses, any materials that are used, and even power consumption if it's a powered device. The sensory component of locomotion is pretty unaddressed by most prostheses. No commercially available prostheses right now actually offer some sort of like natural somatosensory feedback. So that was one of the goals for our research in our lab. So one technique that can be used for delivering sensory feedback is peripheral nerve stimulation. When you apply electrical stimulation to intact sensory nerves in amputees, for example, those signals can still travel to the brain and elicit feelings of touch. So we chose this method to deliver sensory feedback using cuff electrodes implanted on the sciatic and tibial nerves because those innervate still the bottom of the foot. So far, we have implanted this cuff electrode technology in 4 unilateral below-knee amputees. So the next step was to take this peripheral nerve stimulation and actually incorporate it into the prosthesis because standing alone is not going to do any good. It has to be actually tied to the prosthesis itself. So we have a sensorized insole containing 8 force-sensitive resistors that we place in the shoe underneath the prosthesis, and pressure on different parts of that insole is actually tied based on prior experiments to certain electrode contacts in order to elicit tactile percepts in approximately the same location in the phantom foot as the prosthetic foot. So our next step after evaluating that this method was successful and was able to deliver tactile percepts in the foot, we needed to actually evaluate the functionality. Is this actually going to help anyone? But one thing that we were finding is that below-knee amputees, particularly if they're just on one side, can compensate in many tasks using their intact limb and their vision. But that's not going to save them in every task. So we wanted to find and develop a locomotor task that would really sufficiently tax the plantar sensation in just one foot at a time. So we found this horizontal ladder walking test that had been conducted in animal studies before. And this involves laying a ladder horizontally on the ground, and the rungs are randomly spaced apart. And that spacing changes between each trial in order to minimize any effects of learning. So you can't just memorize the course and barrel through it, no matter how hard you try. And then to add an extra layer of difficulty, because I'm a little cruel, we blindfolded them as well. So they weren't able to, use their vision to help, succeed in this task. We conducted the test with 14 able-bodied individuals, again, because it hadn't been conducted in humans before, in 6 below-knee amputees who were not receiving sensory feedback, and 2 of those were the sensory neuroprosthesis users who were enrolled in our primary study. So specifically, those 2 users, this is what their actual sensory feedback looks like. We broke the foot up into 3 regions, the forefoot, midfoot, and rear foot. And when pressure was applied to the metatarsal sensors placed underneath the prosthesis, the participants would report those regions shaded in red here. Same goes for the midfoot, shaded in orange, and the heel shaded in purple there. And the increases in plantar pressure on the bottom of the foot were also scaled to increases in the stimulation pulse width to sort of match increases in force to increases in perceived intensity of the stimulus. So several performance metrics that we used were some insole readings from the actual force sensors in order to determine which region of the foot was used to step on a rung. We also placed video cameras along the sides and the end of the ladder, and we were able to use those to extract trial completion time and the number of errors per trial. For the sake of time, even though I'm already talking fast, I'm just gonna focus on the video recordings for the rest of the talk. Some examples of what foot placement errors actually are just missing a rung entirely, stepping on 2 rungs at once, stepping on the side rail rather than on a rung, or going to step on a rung, shifting your body weight, and then slipping right off. So taking those metrics of the errors per trial and the trial completion time, we know, okay, there's a speed accuracy trade-off. It's something we all know very well. Any tasks that we're performing in daily life, when we start to rush something, we're going to mess it up. So that's something that we predicted in this task as well, and that that trials with a higher number of errors would be the ones that they completed with a lower completion time. And interestingly, this is what we saw with the 6 below knee amputees who performed the test with no sensory feedback, or no more added sensory feedback than they already have. And but we didn't see this trend with able-bodied individuals, which we actually found was pretty interesting and surprising. But this is sort of the performance then that we were able to aim for. We wanted to take the graph on the left and essentially turn it into the graph on the right. Did somebody? Okay.
1 minute.
Oh God. Okay. So our goal was to, again, minimize that trade-off to resemble able-bodied performance. So I show here the dashed lines are the average number of errors per trial and the average completion time for able-bodied people. And we were aiming for that intersection point. And we found with our 2 participants, they were both able to merge towards that point, but in different ways. So one participant had a lower completion time when performing the task with sensory feedback, and the other participant who made a lot of errors made fewer errors when performing the task with sensory feedback. And that's what's shown here on this slide. The top video is him performing the task without feedback, and the bottom video is him performing it with feedback. So making fewer errors, not slipping as much, not skipping rungs, just generally more efficient at performing the task. So in summary, we found that without training, amputees were able to utilize stimulation-evoked touch in a challenging task, and that this shows that sensory neuroprostheses have the potential to improve locomotion for amputees. And the next step is integrating it with motor control. Again, locomotion is a sensory motor process, so integrating this sensory feedback with some sort of motor control over the ankle to have volitional ankle control would be huge. So check out our recent paper and scientific reports on this for way more detail. Thank everyone.
Thank you very much. You're 1 minute longer. So Marcos, let's go in forward, because if not, we finish midnight European time.
Let's do in alphabetic order. Marco, go first.
Okay, I go. So Marco goes first. Then, so my question is, there's a lot behind like the scenes where you would actually have to tune the stimulation in order to promote the actual kind of sensation that you want to have, and that's a super difficult task when you want to obtain something functional, but you don't know how to like directly couple these things, like what the patient might report when you stimulate, what would actually be functional at the very end. So in all of this process of selecting what would be actually the sensory feature that you're gonna provide to the sensory prosthesis, what would you wish could have been easier or better, or in terms of you think that there was just this much missing for having something much better in terms of outcome?
Yeah, well, I think like the biggest thing is the modality of touch that is evoked. A lot of our participants report, actually it's probably the next slide, feelings of like tingling and pulsing, and they report feelings of touch and pressure, but not quite as much as we would like them to. And I think in order, like one of our participants is very okay with that. He says, he doesn't mind, he still likes it. The other participant, he still likes using the device, but says that he wishes that we were able to give a more like natural form of feedback. So we have tried, varying a lot of different parameters like pulse width, pulse amplitude, pulse frequency, and trying different stimulation paradigms that are more like biomimetic. But to sort of minimal success, it's oftentimes like tingling. So I think like that would be the one thing. If we could find the magic algorithm there, that would be great.
Thank you, Marco.
Hey, Breanne, how are you doing?
Good. How are you?
Good. So, we discussed already this when you came at RNEL a little bit. So this time also because you've been toughly and thoroughly evaluated, I'm gonna make a question that is a bit like general and provoking, like in the sense that we saw already this morning from Stanisha some results about restoration sensory feedback, and we also saw in your data sets that there is some improvements that you can actually do see and record for scientific publication. But let's put a second away our scientist hat and put our engineer's hat. I mean, is this really useful? And if not, what's the bottleneck? Is it on the neurotechnology or what?
That's fair. So yeah, that is a big thing of statistically significant versus clinically significant. What's actually going to have a huge impact on them. As I was saying, like for unilateral below-knee amputees, generally they are very, very functional. So I think like the situations where they need tactile feedback are kind of fewer and far between than people with a higher level of amputation. Generally, below-knee amputees can compensate with like vision and by paying attention, any residual proprioceptive and somatosensory inputs. What I think is largely it is that the twofold. One, I think like a more higher level of amputation, I think would benefit really significantly from this type of technology. But I also think that my big thing that I try to hammer in is like the integration with motor control, I think that's going to be the ticket. I think doing them separate, it's great and it has to happen in order to characterize these responses. But like generally, you're going to have the most effect when you combine sensory feedback and active control over the ankle. And I think that's going to be the hit. And if that doesn't work, then ask me in a year.
But when you, Stani, how much time do I have?
Marco, unfortunately, there's a second one, but I really enjoyed your presentation.
Thanks.
Well, okay.
Marco, you know how to reach me.
Yes.
Diplomatically, she would have time for the last question, honestly. Go.
So she has, okay. So when you say, because also Stani, I think, was saying today, and then I was having a private conversation with Mr. Petrini about it. So when you say we need to integrate motor control, what does that really mean? Like, because I think, but maybe I'm wrong, that most of the motor control of the lower limb is reflex-based. So what do I do with the feedback if actually I need to react in times that are so slow, there should be a spinal reflex. So it's not a conscious execution.
Yeah,
For example, a sleep.
Yeah, I think if it's like reactive, then it is a lot of reflexive activity. But generally, if you're just like, if you imagine you're like walking over something that's uneven, that's more voluntary, voluntary movements of the ankle and things like that. So right now it's sort of mismatched that we have trouble evoking feelings of proprioception. And we think that's because, you might be able to feel it, but then if it doesn't match what your ankle's doing, it sort of wipes out the effect. So I think voluntary control is where that's going to matter more so than reflexive. I don't know about that.
All right.
The hard one.
So thank you very much, Christy. Incredibly nice presentation. So we are going forward